The first step in hacking a Wi-Fi router is finding a way to extract firmware off it. In this video, I'm going to show all the steps I use to exfiltrate firmware off a router, from disassembling it to finding a physical interface on the circuit board to using programs on the router to dump the firmware via a UART shell. Additionally, the latter part of this video will demonstrate another method I have yet to see taught anywhere else online. In this method, I'll craft a custom assembly program to dump the firmware over Ethernet, making the exfiltration process take seconds instead of the days or hours that can be required when using UART. I didn't originally mean for the video to go so long, but when I started learning about hardware hacking 8 months ago, I felt like a lot of videos only showed 1 or 2 steps, and I wanted to show the entire process from physically having a router in your hands to having the firmware fully exfiltrated and on your host computer. I'll put detailed chapter markers in the video so you can just skip to parts that you want to see if you already know some of this. Lastly, I want to say that I will expect that anyone watching this video does have a knowledge of the Linux terminal, programming in C, and programming in assembly. I will also be putting any links to tools and code that I use in the video in the description below. Alright, the first step is to get a router. I found a cheap one at a Goodwill nearby. I think that's a great place to find a router. This one was $10, but normally they're cheaper. After you get the router, you're going to want to find where the screws are. Normally, companies that make routers will want to hide the screws because they don't want people opening them up. This one was pretty easy to find, but sometimes they'll be stuck under labels or stickers, so just look around a bit. Once you have all the screws out, see if you can pry open the casing and then see if you can take the circuit board out of the router case. Before going further, I do want to say that the easiest way to get firmware is just to look up the name of the router and see if the company that made it has posted it online. Sometimes you can just download it directly from a manufacturer's website because they'll post it as a firmware update. In addition to finding firmware updates online, you can also find pictures of internals of routers sometimes by looking up the FCC ID. Any device in the US that emits RF waves is required to have an FCC ID, and if you look it up on fccid.io, you can find pictures of the internals often and other documents about the device. But in a situation where you can't find information about the embedded system online, we'll want to start by trying to find a UART header on our embedded device. UART, which stands for Universal Asynchronous Receive Transmit, is a hardware communication protocol. It's often used in embedded devices for things like firmware updates, diagnostic checks during manufacturing, and other communication between chips. But how do we find the UART header? Sometimes it's just labeled on the board. Other times you may find pins on the board that are labeled TX and RX, which can be an indication of UART. Sometimes there's no labels, but the test points may be grouped together in a box printed on the board. However, the only true way to know if any chip on your board supports UART is to look up datasheets for the chips on your board. Unfortunately, this router has a big metal shield soldered to the board that prevents me from seeing the name printed on the microcontroller underneath. I did, however, find some test points on the board grouped into a box. This was a clue to me that they might be UART. Sometimes a UART header on a board may have pins coming out of it, but in the case of my board, there were no pins on the UART header. There were holes that went through the board called vias, but they already had solder in them. I knew I was going to want to connect jumper cables to the board, so I wanted to go ahead and solder pins into the board. The first step was removing the solder that was already in the vias. You can do this with a cheap soldering iron. You don't need an expensive one. It just needs to get really hot to melt away the existing solder. Once I got the solder hot, I used a copper solder wick to remove the solder. Finally, I grabbed some pins and some solder and soldered them onto the board. In the case of this circuit board, I just saw that there was this box around these pins, which was an indication to me that it was a UART header. And then I just hooked up my TTL to USB cord and it worked. In order to interface between our computer and our circuit board, we're going to use a TTL to USB adapter. Keep in mind when you're using the jumper cables to connect the circuit board to the TTL serial adapter that you want to connect the receive pin on the board to the transmit pin on the wire. You don't want to connect the transmit pin to the transmit pin. The first thing we need to do if we're using VirtualBox is we need to make sure that the TTL to serial adapter is seen by the guest operating system. So you're just going to check the box next to that adapter after you plug it in. Okay, now the first step is to make sure we know the baud rate. The baud rate is the speed at which bits are going across the pins on the UART header. There's different standard baud rates that are often used, so you can just Google common baud rates and whatever comes up will probably be good. So I actually just guessed what the baud rate was and was able to get lucky. 9600 and 115,200 are very common baud rates, so in this video we'll see that this is the baud rate. However, if you don't know, one tool you can use is called baudrate.py. Let's look at an example. When you plug in your USB TTL to serial adapter, it's going to become a device in the Linux file system. So that will normally be at this location. So I can see that it's right here. Look, if we disconnect this adapter and then list out those devices again, it says nothing's there. So this is just one way to confirm. Okay, so now we're going to use the baud rate tool just like so. I'll put a link to this tool in the description. All right, so I haven't turned on the router yet, so I'm gonna do that right now. Okay, so look, we can already see that it's outputting data. However, if I click the up or down key, we can see that baudrate.py will try listening at a different baud. Sometimes it will spit out garbage if you're on the wrong baud rate because it doesn't know how to interpret the data coming across the pins. However, see when we get back, when it cycles back to 115,200, when it goes back to that baud rate, it can start reading the ASCII characters that are being sent across the TX pin on the router. Now that we know the baud rate, we can use a tool like Screen or Minicom to talk to the router. So I'm going to use Screen. The way we use Screen is we just give it the device and the baud rate, and then we can receive output from the embedded device and then also send input to its receive pin. So if I do that, okay, sweet. So I hit enter and now I'm in some built-in shell. So, okay, it also looks like it's printing sending discover. That's probably a dynamic host configuration protocol process sending some output. So that's a little annoying, but whatever. So the first thing we're gonna do is look to see if there's a binary on the router that would make it easy to send files from the router to our computer. So how are we going to do that? Well, if there was a tool like file transfer protocol or something like that on the router, then we could use that to send over data. So I'm just going to look around. So all these tools are available for us to use in this shell. None of them are jumping out at me as tools that could be used to send data to our host computer. Okay, so I'm looking at locations that typically have binaries in them, and I found this TFTP, Trivial File Transfer Protocol. It is a tool that's used to transfer files from an embedded system to a host computer. However, I'm going to be honest that I spent at least an hour and a half trying to figure out how to send files with it and was unsuccessful. So if I ever need to use it, I'll spend more time doing that, but I have other methods that work just as well. I also see that there's this hexdump binary. So this is just a hexdump utility. You can use it to dump the hex of a file. Okay, so right here I have a file called firmware version that just has the version of the firmware. The hexdump, it just prints out in hexadecimal format the entire file. So this is great because we could use this hexdump on any file I can just save this hex output to my computer and then use a different utility to turn it back from hex into the original file. So first I'm going to exit the screen utility by pressing Control A and then hitting K. It'll ask me if I want to kill the window. I'll say yes. Okay. So now if we look at the manual for screen, we can see that if we use the tac, I think it's the tac L option. So we can use tac L to tell screen to record or log the output to a file. And then we can use the log file. Okay, so I'm gonna use screen, then the device, then add the option for logging. Okay. Let's pick a binary that we want to export. I don't know, let's see how long this if up file is. Okay, perfect. It's only 435 bytes. All right, so I'm gonna hex dump it like so, if up, perfect, and we're done. So now I'm gonna exit screen, and here is my output. So now if we look at it, we're gonna see, yes, whoa. Okay, I'm not sure why it has all these escapes in there, but that's fine. The point I was gonna say is that there's gonna be a lot of extra garbage from when we were typing around. You know, it's still recording everything that we're seeing, but we just want this hex output because we're just trying to figure out what's in this file. So we're gonna need to clean that up. So I'm just gonna open it in Vim and then highlight all the lines. You can use any text editor to do this though. I'm gonna highlight all the lines up to the hex dump and then delete them and delete this line. And it looks like this line doesn't contain any hex output either. Bear in mind that only these columns are the hex dump. This is just the offset from the beginning of the file. All right, so looks good. I'm gonna save that file. All right, now we're gonna use a utility called xxd to turn this hex output back into the original file. So we can do that by using one of the command line options. I'm gonna have to look at the manual to see which one. I think it's tac R. It is, so let's just try xxd tac R screen. I think I have to cat it to a file. I'll call it if up. Let's just look at it using less. Looks about right. Okay. How do we know that if up is exactly the same as it is on the embedded system? Well, we can do a hash of it. Okay, this is the hash. Lots of embedded systems will also have a hash utility on them. So let's see if our embedded system does. You can also check the size of the file. So I'm gonna check an if up. Oh, okay, it looks like it's 1 byte too big. Not sure what happened there. Here, let's look at if up. Is there like 1 extra byte at the bottom? Oh, it looks like, okay. I don't know what this is. I'm just gonna delete it, see what happens. Let's take that hash again. Okay, so here's the hash of it. I'm actually going to open tmux so I can get 2 side by sides. And here is the hash of if up. Now let's connect with screen via USB, the embedded system. Okay. If up, yeah, it's right there. Okay, and D5 sum if up, and look at that. So the hashes are the same, so it is indeed exactly the same bits on our host computer. So we just figured out a way to exfiltrate a binary from the embedded system to our host computer. However, there is a problem, and that problem is that it's going at, as we saw, a baud rate of 115,200 bits a second. So that is very slow when we're transferring large files, and we will be transferring large files. How large? Well, let's go find the root file system. Okay, so when we list everything in proc, this is one thing we're going to want to look at, MTD. That stands for Memory Technology Device. You don't really need to know what it is to follow along in the video, but it is essentially a device file in Linux, kind of like TTY USB 0. It's something that the kernel uses. It's an abstraction layer between hardware specific devices and higher level applications. So applications can use MTDs to talk to hardware memory devices, but it's not really important. We're going to look at cat MTD, and this is what we're looking for. Specifically, we can see that the root file system is located at device MTD2. So what that means is if we go over to the dev directory, we can see MTD2 is right here. So now let's say we tried to hex dump it. What's going to happen? It just keeps going and going and going. This file's massive, so I'm going to stop it. So now that we know that the root file system is at MTD2, we can try using hexdump on it. First I need to make sure I'm gonna restart screen, tell it to log the output, tell it to use a log file called rootfs, and then give it the device and the baud rate. Okay. And now we're just going to use hexdump on MTD2. And this is going to take a while. Why? Well, while that's going, let's look at some math. So 3.6 megabytes, and 3.6 times the size of a megabyte is 1024 to the second. So we have that many bytes, and if we multiply that by 8, we'll get the number of bits. If we divide the number of bits that we're trying to exfiltrate by the bit rate, then that will give us the number of seconds it's going to take, 262, which is, if we divide by 60, 4.3 minutes. So this is going to be going on a while. I'll come back when it's done. Okay, I'm back and the hexdump has finished. So now we can exit screen. So now we're going to use a tool called binwalk. What binwalk does is it looks at a binary and looks for any files inside of it. The TAC-E option is going to tell it to go ahead and extract the files that it finds within the file that we give it. So I'm going to do that. I forgot to trim the file because remember, we don't want this part at the beginning. So I'm going to get rid of that. I'm going to go to the end of the file, get rid of this line and this line. All right, save it. Okay, so now we have the root file system and its hex output, and we're going to use XXD to revert it back to its binary format. So we're going to, by default, XXD will just output it to standard out. So we're going to redirect it to a file called rootfs binary, let's say. And now we're going to use binwalk with TAC-E to tell it to extract files. And looks like it's done. Okay, so let's go and looks like it extracted them here. So we're going to go into that directory. Okay, we're going to go in there, and then we're going to go into here. And here is the file system. So this might look familiar. You can see the firmware files that we saw earlier. So that is the first way to extract a file system off an embedded system. However, there's a method that I have not seen taught anywhere else on YouTube or online that I think is worth showing how to do. We were lucky in this example in that the file system was about 2.6 megabytes. And so it only took me about, it felt like about between 5 and 10 minutes to exfiltrate the file system. However, sometimes the file system is going to be a lot larger, especially this router. This one's about 10 years old, I believe, but newer routers or different embedded systems might have much larger files that you're trying to extract. So what do we do in a scenario when UART is going to take days to send the file using a hex dump? In some videos I saw people just say, okay, I'm going to come back in a few days, see you later, and then they just come back. Now it may be that is your only option, exfiltrating over UART, in which case you might just have to wait a really long time to exfiltrate whatever you're trying to exfiltrate. However, if we're trying to extract firmware from our router, then another option is to do it over Ethernet, because after all, Ethernet is a much faster communication protocol than UART, and our router has an Ethernet port. The problem is that we don't have a program that does that on the router. However, what if we write a file and then put it on the router to do that? And that is exactly what we're going to do. So if we want to look at another way of exfiltrating a file that's much faster than hex dumping it, one thing we could do is we could write a program that listens for an incoming connection over Ethernet and then put that program on the router. So we'll run that program on the router using the UART shell. That program will read a file from standard in on the embedded device and then send that file over a socket to our host computer. So to do that, we can use the echo command. And this is what I mean by that. So if we use cat to read this device, then over here we can just, write some word like hello, write that to dev tty USB 0. It gets written over the UART connection to the embedded device. The problem we're trying to solve is how do we send a file from our host computer to the embedded device? Well, one thing you can do with echo is you can use TAC-E. We can even send characters as hexadecimal numbers. So for example, 41 is a capital A. I can pipe that to write that to dev tty USB 0. And look, okay, an A is written over UART to the router. We can write a Python program that reads a file and then prints it in hexadecimal and then writes that to this device. Okay, so I already wrote a program to do this. So the source this is the file that we want to send to the embedded device. Destination, this is the destination on the embedded device. This is the destination that echo sender is going to write to. So when an echo sender crafts the echo command is going to use the double greater than sign to append data from the file to a location that we give it. See, it's using this command line argument. So what's going to happen is I'm going to create a file called hello world that contains the phrase hello world. All right, so for example, I'm going to do echo sender, and then the file I want to send, hello world, I'm going to write it to the location hello world on the router. And okay, so if I send it now, we can see that the program wrote this echo command and printed it to standard out, but we don't want to print the standard out. We want to write to the embedded device. So I'm going to run it again, but this time write to dev tty USB 0 with cat open on the right side. When I run the program, we see that it indeed wrote this echo command and wrote it to this location. Oh yeah, I forgot it was in cat. Opening it in screen. Okay, if we just look at this location, it is indeed there, and it has our hello world message. Okay, so now we have a way to write files to our device. One thing to bear in mind is that this method isn't super fast because again, it's going over UART. Also, in the Echo Sender program, we have this wait time. This is the amount of time that our Echo Sender Python program is going to wait between sending each chunk of 16 bytes. The reason that there's a wait is because there's a buffer on our embedded device that is getting written to by our host, and then the embedded device is reading from. But sometimes if you don't have a wait time, then your host device will write too quickly and you'll run out of space in the buffer and not all the bytes will get across. So now we have a way to write files to our device. The next step is actually writing the program to put on the device. So how are we going to do that? Well, I'm all for shortcuts. So let's see if we can use Bing Chat to write us a program. That was my first thought. Let's just write a program in C and then compile it for the architecture of our device, which is MIPS, and see if it can do what we want. So what do we want our program to do? Looks good. Oh, wait, let's see if this looks good. Nothing's jumping out at me as wrong. All right, so I'm gonna copy that and create a new file called extractor. I'll call it foo.c. Okay, I'm gonna paste that. All right, and now let's compile this. So now, before we compile it, we need to know the architecture of our embedded system. If we go back over here, let's look at CPU info maybe. Okay, yeah, so this is saying MIPS. All right, so when we're compiling our C file, we also need to know if it is a big endian or a little endian system. You can just try running a big endian or a little endian executable file on the router. That's a valid way to do it, so I'll just do that. Also, sometimes you can log the startup script of the router and it might tell you the endianness of the system. This is a big endian system, so that's how we'll be compiling it. So I'm going to do mips tac linux tac gnu tac gcc. I'm going to use tac o to name my executable foo, and then foo. Okay, so let's look at the size of foo. So that's not too big. That's definitely something that we could send across to our embedded system using our Echo Sender Python program. The problem is that this is a dynamically linked executable. Furthermore, this is telling us that here is the dynamic linker that this file is going to try to use. I don't even know it dynamic linker is on here. This is using this dynamic linker, which is not this one. So right off the bat, I know that when I try to run this file on this embedded device, what's going to happen is the embedded device is going to try to use this dynamic linker to start interpreting this file, and it's not going to work because this file is expecting that this dynamic linker is used, but this is using this ld tac u clibc. So if you wanted to, you could use some tool chain or cross compiler to make this foo file so that it uses this interpreter, but that's more work, and furthermore, you would probably want to statically compile your executable. So getting that library to work with our binary that we're cross compiling can be a little hairy. So we're just going to skip all that and statically compile our binary. We don't need to do any library calls because all the library functions will be compiled into the binary. So let's try recompiling this file, but this time do it statically. Okay, so remember before our file was 6,532 bytes. Well, now it is 667,788 bytes. So what we can do is actually write this file in assembly. And if we do that, then without any error checking, without any libraries, then we can compile this to be really small. So I already have a file that I moved over here that I wrote earlier called extractor ASM. How would you go about doing this if you don't have any experience writing assembly for MIPS? Start by identifying the main task you want to do, make a TCP socket, set the socket option. I won't go through how to write this whole file, though I expect if you've written assembly before, you'll be able to read through this and it will make sense what I'm doing, especially with the comments. I will explain some things that tripped me up when I was doing this. So when you're programming in C, you would use this AF inet to say that you want to use a IP4 family socket. But how do you know that this macro correlates to the value 2? Because we can't use this macro when we're writing assembly. So we can actually go to this website that's called Bootlin, and you can select any version of Linux. So I'm gonna select our version, 2.6.31. However, for what I'm about to show you, it probably doesn't matter which version you choose, because things like because a lot of macros might not change between versions. However, just to be safe, I'm just going to go to 2.6.31 because that is the version of our system. You can use the search feature over here. Just type in AF inet, and then it says, oh, it's defined right here. So I look and AF inet value 2, perfect. And that's what I have right here. There were some that were a little trickier to find. I just had to look around a little harder, but yeah, just use the search feature. So that is one way you can find all these values. So now we're using syscalls for every function that we're calling. So for example, right here, we're using 4169, which corresponds to sysbind. Again, if you don't know that, you can go to the source code, sysbind. The sysbind is going to be in a architecture specific file. So here I'm seeing a number of MIPS file in this architecture directory. I have a 32-bit system, so I'm gonna click on this one and look at this. So these numbers on the side are telling me what number corresponds to these syscalls. So sysbind is 4169. If we look over here, we can see, yep, 4169. Another thing you can do is open up Ghidra. All right, now I'm going to import into Ghidra this foo file that we looked at earlier, that we compiled earlier. All right, open it up. And so now what we can actually do in Ghidra, if we just find that bind call, look at that. Here we have the syscall. We can see that it's loading an integer into this v0 register, which the v0 register determines what call the syscall is going to do. And if we hover over this hexadecimal, we can see right here that it is indeed 4169. That is indeed the decimal used for the sysbind. So that's kind of two ways that I use to find syscall numbers. Okay, we have our assembly file right here called extractor. Now let's compile it and use optimization options to make it as small as possible. So I'm going to use the MIPS cross compiler assembler, and which is going to assemble an object file for me. I'm going to call it, oh, I got it right here. I'm going to call it extractor.o. I'm going to use the optimization for size flag, and then make it. And it is right there. Now I'm going to use the linker and use the O option to name my final executable extractor. I'm going to tell it, use tac s to tell it to not put sections into the final executable that aren't used. And I'm going to use tac os to tell it to optimize for size. And let's see the final size of our file. 764 bytes. That is really good. That is going to be sent basically instantly to the router. Okay, let's send it. I'm gonna name it extractor, and just because I'm curious and want to see it come across, I'll do that. Okay, now let's send it. And okay, it's not instant, but it's pretty fast. And it should be done. All right, let's just ensure that the file we sent was the exact file on this side. So now let's do MD5 on the router side, extractor, and they are indeed the same hash. Next, you're going to want to grab an Ethernet cable and plug it into your router. I'm going to go do that right now. Make sure that when you're plugging in the Ethernet into your router that you don't plug it in the spot for the modem. So on my router, the modem input is yellow, but all the other ports are black. So just make sure you put it in a black port. All right, so remember where our root file system is. It's at MTD2, which is right MTD2 right here. All right, so now we're going to cat that file. So now we're going to cat that device MTD2 to our program. Now we're going to come over here, and this is cafe in hex, but as decimal. And then we're going to pipe the output to, I'll call it MTD2. Okay, looks like it did finish. Let's look at the size of MTD2 and then compare that size to rootfs binary, which is the file that we got through hexdump earlier. And they are exactly the same size, so sweet. Let's just do a hash of them. Okay, so they're exactly the same. Perfect. So I've already showed earlier in the video how to use binwalk to extract files from that, so you can go look back and look at that. But we're done. That's it. What motivated me to use this video is that I hadn't seen people using the Ethernet exfiltration method. If you want to see other methods for exfiltrating firmware, I would recommend checking out Matt Brown's chip-off firmware extraction, where he uses Universal Programmer, and also check out how to extract firmware using SPI NOR Flash from the Flashback team. Hope this video was helpful, and I'll try to answer any questions in the comments.